Okay, let's begin the last tape. Let me just set up my pointer here. Okay, so the last thing we're going to talk about is heterocyclic aromatics. This is where we're going to use the lone pairs of heterocyclic rings, of nitrogens, oxygens, and sulfurs primarily, to continue the conjugation, just like we had been doing with carbanions before. So the first compound we're going to look at is just this simple compound here called Parole. Okay, Parole is a 5-membered ring with a nitrogen and 2 double bonds. This nitrogen here contributes to aromaticity. Okay, and you see that with the structure immediately below it. Okay, so this is Parole with the pi bonds and lone pair just drawn as p orbitals. And here you can see the cyclic array of 6 pi electrons. We say this compound is isoelectronic. It has the same electronic configuration as the cyclopentadienyl anion, which you saw in the previous tape. Okay, so we can use the lone pair of a heterocyclic ring to contribute to aromaticity. We can also have nitrogens substituting for carbons in benzene rings, and in this case, let's look at pyridine. Okay, so pyridine, you may think it looks at first like this has 8 pi electrons, but let's just look at this pair of electrons here. It's located in a place where it's actually not contributing to the aromatic system. Here's the structure of pyridine. And what we see here is we do still have the 6 pi electrons, and these come from the alternating double and single bonds that you see in the pyridine structure. This extra lone pair right here is not part of the aromatic system. It's outside the aromatic system. It does not have any overlap with the electrons in the aromatic system, so we say it's non-contributing. This is an sp2 orbital. This is an artifact of sp2 hybridization, and this orbital here is not overlapping with the pi system at all. We're going to use the word orthogonal to describe the relationship of that lone pair to the rest of the pi system. So throughout the rest of this, we're going to refer to nitrogens as being Parole-like if their lone pair is contributing to the aromatic system, and we're going to refer to them as being pyridine-like if they're orthogonal to the aromatic system and not contributing. The big difference between Parole and pyridine is that in Parole, there are no double bonds to nitrogen, and in pyridine, the nitrogen is part of a double bond. Okay? Let's get some more heterocyclic aromatics. This is furan. Furan has 6 pi electrons as well. Here we have 2 lone pairs. And one lone pair contributes to the aromatic system. This one is part of the aromatic system, whereas the other lone pair, this one, is orthogonal and not part of the aromatic system. Okay, so these lone pairs have different roles, and don't be confused when you're asked if something like this is aromatic. Just from common sense, it would be impossible for both of these lone pairs to contribute. Let's just look at how ridiculous a structure like that would be. Okay, we'd have to say that we had a structure like this if both lone pairs were contributing, and we could all probably say that, okay, this sucks. Alright, so that would not be a good structure. So this would be just a totally ridiculous way to represent lone pairs. Okay, so we can never have both lone pairs of an oxygen or a sulfur contribute to the aromatic system. Okay, let's look at another compound. This is imidazole. Imidazole is kind of interesting here in that one lone pair actually does contribute to the aromatic system. This one, and we say that this one is Parole-like, whereas this one here, notice that nitrogen is now part of a double bond, and this lone pair is orthogonal to the pi system, and we say that this is Pyridine-like. Okay, so this is also a 6-pi electron system and aromatic. Okay, let's look at another system here. This is oxapine. Oxapine is an anti-aromatic molecule. It's actually quite unstable, and you could say, why not just use all 10 pi electrons? Well, again, there's this ridiculous structure you would have to write if both of these contributed. So only one of these can contribute. Okay, can contribute. And thus, we end up with an 8 pi electron system that's anti-aromatic. This is actually a very unstable molecule. It prefers to isomerize to this highly strained structure over here. Okay, so let's look at some more questions here. Let me just back up here for a second, okay? This is kind of where I'm going to end the discussion of what makes a system aromatic and what does not. The rest of this presentation is concerned with the types of problems you might see. And as I said before on an earlier tape, every one of these is going to have basically the answer, this one's aromatic, these other ones are not aromatic, and therefore the aromatic one is better. But let's look at first type of problem we might have. Underneath each compound, write yes if it contains an aromatic ring, and no if it does not. Okay? And I'll advance the slide to another one that actually has the answers on it, but let's just go through what we would think about. This is no, not cyclic. Okay, if it's not cyclic, we can't be aromatic according to the theories that we've presented so far. Okay, what about this one? Well, this one is also no. This is 8 pi electrons. This is completely isoelectronic with this compound. It's no, for exactly the same reason. Boron is kind of interesting. Recall that the structure of BH3 is this with an empty p orbital. Thus, we have an empty p orbital here, and this is actually aromatic. It's 6 pi electrons. Okay, the dicyclobutadiene dication, this is yes, because it's 2 pi electrons. Cyclobutadiene dianion, also yes. It's 6 pi electrons. We get 2 here, 2 here, and 2 there. That adds up to 6. Every one of these nitrogens in this compound here is part of a double bond, thus they're lone pairs or are orthogonal to the system, and this is yes, 6 pi electrons. Each of these is orthogonal. This nitrogen here is part of a double bond, but actually both of these nitrogens are part of a double bond. So these lone pairs here are thus also orthogonal. Only this lone pair counts. So this is yes, and this contains 6 pi electrons. Let me just show you another trick question I've done in the past here. Sometimes I just write this word here and ask you if this is aromatic or not. Of course, you should say yes for graphite because it's just a bunch of benzene rings fused together. Okay, so this just is a slide that just tells you the answers of what I presented in the previous slide. Okay, let's look at another problem. Which nitrogen in pyrazole is more basic? And of course, the bulk of the credit from this question would come from answering the question why, since you have a 50% chance of getting it right without knowing anything. Okay, so if we look at the lone pairs here, basically this one is part of the pi system. Sorry, this one is orthogonal. And this one is part of the aromatic system. So which lone pair is more basic? Well, that one. The one that's orthogonal. And why? Think about the protonation products, okay? When you add a proton to this nitrogen right here, this is what you get. And this one is still aromatic. If you count the lone pair, it's 2 from the pi bond there, 2 from the pi bond. This one has 6 pi electrons. This one is no longer aromatic. There is an interruption in the conjugation. Okay, there's no lone pair at this nitrogen, and thus there's nothing to continue the conjugation in this system. Okay? Alright, so the nitrogen that's part of the double bond, or the nitrogen that's orthogonal, is the more basic lone pair in pyrazole. Okay, let's look at another question. Which of these Diels-Alder reactions is going to occur at the fastest rate? Predict the product and predict which one is going to occur at the fastest rate. First, let's look at the two products. There's product number 1 and product number 2. What you can see here is that in the top case, what we've done is we've taken something that's weakly aromatic, 10 pi electrons. Let me just add something here I may not have gone through before. There's this place where you touch this pin. Okay. The amount of aromatic stabilization of benzene is a lot greater than there is in any of the other heterocyclic compounds. So benzene aromaticity is still much higher than anything we've encountered so far. So this is weakly aromatic, and this generates a benzene ring which is highly aromatic. Okay, this is weakly aromatic, and this takes us to a compound where there isn't any aromatic ring present at all. So we kill what little aromaticity we have. And of course, we have to say that the top reaction is more favorable, okay? Because if you look at what we do in the way of creating or destroying aromaticity, we create a lot of aromaticity in the top case, when we go from here to here, and we destroy any aromaticity that we have when we go from here to here. So it turns out that the bottom reaction here actually can be reversed to some extent very easily. Okay, so the bottom reaction isn't nearly as favorable as the top reaction. Okay, this one I'm asking you to place 4 alkene groups in an orientation where you can get a completely aromatic system and predict which of these is going to be the more stable compound. Okay, so if we do that here, and let's remember that we have lone parent nitrogen, we would put those here, 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 and here. Okay, and this is isoindole, and this ring system here is just called indole. It's a Parole fused to a benzene ring. Okay, so in isoindole, the only aromatic ring we have is the Parole ring, or we could say we have maybe a 10 pi electron system here, whereas here we actually have 2 aromatic rings, a Parole ring right there, and a benzene ring, the best aromatic ring of all right there. So indole is the more stable compound. Okay. And the stability of these 2 compounds is not really comparable. Indole can exist at room temperature for a long time, whereas isoindole reacts with itself and does a few other things. It's not doesn't have an extensive lifetime at room temperature. Okay, let's look at one other case here. Carbonyl compounds are polarized as partial positives at carbon and partial negatives at oxygens. In the extreme, we can represent them by the polar resonance form in the box shown here. Okay, normally this is not a good resonance structure, but it explains the reactivity of a carbonyl system very well. Okay. All right, so which of these compounds, A or B, is more stable? Actually, sorry, let me rephrase the question. You already see which one is more stable there. Explain why compound B is a lot more stable than compound A. Okay, if we draw these resonance forms here in A and B, we can see that the resonance form of A contains a ring system that's only 4 pi electrons, whereas the ring system of B contains a 6 pi electron system when we write this other resonance form. So B, the carbonyl group's polarity, sets up an aromatic resonance form, whereas with A, the carbonyl group's polarity sets up an anti-aromatic resonance form. Okay, so thus compound B is a lot more stable. Okay, so this is where this tape ends. I apologize to everyone for abandoning you, but I hope that you, from these tapes, have learned enough about aromaticity that you understand the concept of how important it is in determining the reactivity of organic compounds, and perhaps most importantly, I hope that you all do well on exam 5 and quiz 9, which involve these concepts. Okay, so I'll see you all after Thanksgiving.